Hello, this is Kishore Kulkarni from Denver, Colorado. I'm the president of Society of Indian Academics in America, and what we are going to see very soon is a excellent presentation by Dr. Nanasaheb Thorat of University of Limerick in UK. He's going to talk about the cancer research and a few other things that his lab is doing in the UK. And Dr. Thorat is a world-renowned cancer researcher, originally from Kolhapur area of Maharashtra in India. And I'm very happy that he has accepted our invitation to talk in our webinar series. So you will love this webinar. I know first part of this webinar is a little bit cut off, but we will join it in a regular 40 minutes presentation after about 8 minutes of cutting in there. In any case, enjoy it, and if you have any questions, call us or find me at www.siaaus.com, and please attend our future webinars. Very good. Thank you. Bye-bye.
Single rule: stop, go, and wait. Well, this is what the phenomena in biomolecular science we call the apoptosis, where cell start to grow, they know where to stop and when to die. That divides, everything works. But this is corrupted version, like bad driver. They make the problem and they comes to the damage control for that. But usually cancer cells, when they have the damaged DNA, that damaged DNA makes the protein, a new layer of proteins, and they makes actually a shield to the tumor. And we cannot kill them easily because our immunity cannot recognize them in very initial stage or even late stage also. And sometimes we improve immunity, that's very, very late, that to encourage immunity to attack on cancer and kill that. So now this is what the real problem in cancer actually. And as a clinicians, you might know about it, that this dominance is actually parasite dominance, like the Korean movie. As we know this movie, like, and this is one of my favorite movies also. Why it is? Because this movie tells about like the poor people, the fight between poor and rich people. Actually, when you give some space to some people, they want to occupy the whole space, yeah? And they try everything to do that. So like this movie tells about that. In Korea, I lived there for 2 years, and I know, like in Korea, it is a real story. Like people are very poor also, and people are very rich. Even we say like Korea is very well advanced, or the poor index is less, but it's not. I saw many poor people. They are begging, they are selling stuff on the roads. It's everywhere. But the Korea is one example because it's evolved in last I will say, in last 30-40 years, and this is witness of parasite dominance. The same happens in our body also. Like these cells start to grow and they behave like a parasitic, and they occupy everything. Even not occupy, they have like a brain, they control, like they enlarge and they make the angiogenesis, like some blood vascularization, and they take the nutrition from the blood at a certain stage, and they grow fast, and the tumor goes spread big. And not only tumor, but cells goes into the blood. They don't survive easily. Actually, out of 1 million, only one cell can survive in the bloodstream, but they go and they stay somewhere else. Like this metastatic works. And metastatic is not just a behavior or the intrinsic property of cancer cells. Actually, some of our organs, right? 4 years ago, there is a publication in a high quality journal that even liver cells are doing metastasis, even normal cells also. Like liver cells go somewhere and try to occupy that space or survive there. But because this is not cancerous cells, usually they don't get the space there. But unfortunately, cancerous cells get the space. The other organs, like breast cancer, goes into the bone or the brain. Like our work is more on breast to brain metastasis, and they survive there. So this is what the story about how cancer start, and how survive. We know we have these therapies already available, chemotherapy, we have radiotherapy. This is standard care with surgery. This is what we are working at the lab, like immunotherapy. So as I said, like in immunotherapy, you have to train your immunity to kill the cancer cells. But why it's not happen? Because they have different proteins on the cells or on the whole tumor, and then immunity cannot recognize, and they treat them like our normal organs. Some immune cells are also within the tumor. Also, they survive there, but tumor is dominant, so they don't allow that immune cells to go and kill that cell. So this is what happens in all therapies. Now immunotherapy coming, I will come to that. Mm, I'll not go for detail, but what happening in the cancer research is the era. Like earlier, they think that it is a biochemical pathway. So there is something difficulty in biochemical ways. That is biochemistry era. Then late 1980s, people think or 70s thinks that this is genomic era. Like it is because genetic problem. But after 2005 or 10, mostly people thinks that it is a metabolomics or metabolic disorder. And now people talk about, oh, this is just actually metabolic in cancer is. But I would say like they are the combining of all these three at now. So it is metabolic also, genomic problem is there also, but biochemical problems are there, biochemical pathways are there, and they play a major role also in cancer progression, like nutrition or the energy metabolism. Mhm. This is what the usually the growth cancer drugs market is available. We have right now 900 drugs already available in chemotherapy, or some are in immunotherapy. Now, I'll come to this is why how my journey started. Like I'm a physicist, and how I came to the more in biology or molecular biology or preclinical stage. This is very interesting guy. So I love him like because he is a true anthropologist earlier, and he studied the mummies and other genetic materials because anthropology is more work there. And he understand, okay, this is what happens with the Neanderthal or others. And then he come back from Egypt, and because he understand that my knowledge is very limited to do something different in this field. And then he took the medicine degree again, and he studied medicine. He went back with the same organization to study the mummies, and he took some kind of a Neanderthal DNA, and he grown the mini brains in a uh, with the Neanderthal DNA. Now this is true, like because he got the Nobel Prize in 2022 during the peak of the COVID. Why? Because in COVID, you might know, like we have many scenarios, like husband got the COVID, wife don't, children don't got the this COVID, or many people have these scenarios, multiple scenarios, from where it comes. Then his theory was that it comes through your brain. Actually, immunity is controlled by your brain, and this is what who has a better immunity, who have those have the well, and it all comes through the brain actually. That's why those people are very silent, not living in very stress environment. Their immunity is always better than those people even taking the immune boosters and all this, but they always in stress. Their immunity is weak, and he proven this. Actually, his theory is proven during the COVID. That's why he got the Nobel Prize. And then I realized that if he makes the mini brains in a lab, why don't we go and understand what is real problem in cancer right now? Industrial problem, especially the main industrial problem in cancer is industry has a drugs, but they don't study the more fundamental way. Why metastasis happen, how tumor grows, because all 900 drugs in cancer, what is the story? That these drugs are mostly out of that, I would say 80% drugs are for primary tumors. They evolved as a primary tumor or discovered as a primary tumors. But if you know that most of the time we diagnose tumor in late stage, in metastage or late stage, stage 3 or 4 usually, not in primary stage. So we have drugs for primary stage, but we don't have diagnosis there. We have diagnosis for late stage, but we don't have drugs there. And we are treating the late stage cancers with the primary tumor drugs, so they won't working. Also, why metastasis happening? Why tumor cells are growing others and surviving there? And then we decided, like, can we design this kind of 3D models to understand why these metastases work, why drug fails, how they fails. And this story started when I was in Oxford. Before that, I was more focused on the energy-based cancer therapies. And then I come to the clinical setting, preclinical settings, where we started to develop actually a kind of a platform. So many people are working here. Usually in industry, this works like they have the target for any disease. They understand disease, not industry actually. Most of the university scientists, they usually are clinicians, especially in health sectors. They understand the disease and they know that there is no cure, no treatment. And then they go for scientists, okay, this is what we have to discover. It may be a molecule, it may be any therapy, any kind of medical device-based therapy, or maybe a chemical-based therapy. And then it is a target identification, lead discovery by chemist in the lab, and then goes for pharmaceutics for optimization and preclinical testing. Then phase one, phase two, where clinical people mostly involved. It is a multi-billion-dollar investigation along with the time. Usually I work in this field as a core researcher, and somehow now we connected with the industry. We know how the failure is. Now, most of the failure is in preclinical testing. What happens here? So we test the drugs, especially on the animals, in cancer also, where we induce the tumor to the rat or to the mouse or the other animals. Right now, dogs are the natural patients who can get the cancer. But the pathology or the physiology of these animals is far different than the human. Human is very complex. And then we're testing these drugs and we are inducing tumors. So induced tumors doesn't have the same molecular feature that the natural patient has. So that heterogeneity we cannot play in drug discovery, especially in preclinical testing also. And that's why most of the fails when they go for the human, because we have induced models. Very few natural models available, but whole industry still rely on the induction of the models. Now, this is the main problem right now, and that's why this preclinical test fails in the humans. And now the world is going into the, can we design this kind of human anatomy, physiology, microenvironment, everything, a heterogeneity into the lab. And this is what the next level, that is understanding the main problem, the failure, and better to go for again in the lab and do something different, which is more compatible to the human. So now people are developing the 3D models, multidimensional models of the cells, and then human patients also, and testing the drugs. And then from that, we can make the report, the scenario. Instead of going for animals, we can directly test them onto the, or go for the patients. This is one, the personalized way. We are working on that. Another also, we have drugs available, but we do not have the carrier available. The carrier is the the problem that drugs don't know where to go. Yeah, they will everywhere in the blood, and then they go for filtration through our pathway. Sometimes they stay, and if they stay, they make the side effects. And out of, let's say, 100 mg, out of 100 mg, only 5 mg can reach to the tumor, even less than 5 mg. And this is very less localization into the tumor, and that's why they fails. That's why we need the carrier. We can bring them to the tumor and will release that drug. We don't need new drugs actually in the cancer. Nobody is now working on the new drugs in cancer, either new treatment modalities or totally shifting on the genetic or the gene therapy base or the personalized therapy, but not on the chemical based drug discovery, because they know the failures. Either they are now developing the carriers to target drugs into the tumor. So we work on this also. My team also working on the similar kind of drug discovery. Lipid is now my focus because it is already FDA approved. Also, I'm physicist, so we know the problem in diagnosis. Diagnosis, we still rely on the, for cancer, like either you have to go for biopsy and they'll go for histopathology in the labs. Histopathology don't give you any molecular texture of cancer. It is either cancer or non-cancer, that's fine. Now we are doing more hormonal and other genetic test, or maybe some biochemical test, but still rely on the chemistry for that. Chemistry always play with the compounds, and when you treat with any chemical, they change their features. So that's why even if we go to know about many molecular features of the tumor from patient, but because this is by the chemicals, and that's why they change much of information. So there is a solution for physics like Raman spectroscopy. You might know about Raman, who discovered the theory 100 years ago. We use Raman's techniques. What Raman does actually, Raman is just a laser-based technique. You just shine laser on some compounds, and at the return you get the some molecular information from that compound. It's very critical data, complicated data. You have to analyze it. From compound, you can go up to molecular level, not in the atomic level, but up to molecular level, how molecular behaving there. Now, the same technique we are using in the lab also to understand the molecular feature of cancers. And that molecular feature, yeah,
I have a question. This
yes,
this Raman thing comes from Dr. Raman, who got the Nobel
yes.
Prize.
He is
Yes,
Okay,
yes.
discovered.
okay.
Yeah.
That's
And
what he's named after.
yes, yeah,
He
that's
might have
right.
been the
So
first Nobel Prize winner from India in physics.
yes, yeah, he is the only actually who got the Nobel Prize working in the. He
Correct.
discovered all these his theory in India,
Yeah.
and
Okay.
you will surprised to know that I was involved in the one action. We have 250 scientists from Europe, and their name was
Hmm.
Raman for clinics. Like
Oh,
Europeans are more discovering about Raman than Indians,
then
and
Indians are. Yeah.
yeah, we have very high-end lab for Raman spectroscopy. You'll surprised to know that we have 5 million projects from European Commission
Oh,
for only on Raman, and we are discovering the
oh,
molecular feature from cancer. So
got
here
it.
we get the data, which is very complicated, but it is molecular level. So from what we
Hmm.
can diagnose, like cancer patient samples, we can understand the molecular level. We can actually get the proper diagnosis. What is the heterogeneity? What exactly the problem in proteins or other stuffs or biomolecules way or bioenergetics, like how their energy metabolism working there. And Raman is giving that information. So my own research area is in these three fields. One is detection by Raman, developing cargoes, and developing the models. So also earlier, actually, I shifted from this field, like I was using the nanomedicine or the energy especially. So earlier, as I said, like 10 years, I was working almost on the energy-based therapies, where you can, like for example, MRI is the magnetic field-based imaging technique, where we use the echo to get the image. But that has the high strength magnetic field up to 1.5 Tesla. We are now functional MRI up to 7 Tesla. But the same field, if we reduce some field and use, because magnetic field, we can target on a specific organ. Uh, and if you use some magnetic materials, because magnetic material has a functionality under the alternating magnetic field, they generate the heat. And when they will generate the heat, that heat can be utilized to the surrounding cells to dye them or to kill them. This is called the magnetic hyperthermia therapy. I was working that, still I'm working on it. There are some couple of instruments comes into the clinical stage. Still there are regulatory barriers, but hopefully in next 5 to 10 years, we will see like along with radiotherapy, there will be a magnetic hyperthermia therapy also, which is very localized. So you can target tumor with the magnetic particle and then apply the magnetic field. Magnetic field only excite the area where magnetic particles are. And this is where in the tumor, and they will kill that. But with the temperature effect. You can also do the light also. So like a laser light with the plasmonic material, like gold nanoparticles are the one example. They absorb the light and they generate the
Hmm.
heat. Even they absorb our visible light or the infrared light also. Infrared is very effective because infrared can penetrate into the but has the very limitation. They don't penetrate into the skin. So this is what we also doing. We have sophisticated lab for these two setups also. This is my prime area. Now we are developing this kind of materials. I will not come to very scientific part, but I will just say like this is what the nanoparticle, nano cargo we are developing. So for example, this is core area. where they have magnetic particles on that gold, so they can be excited magnet and gold also. And this is what the biomolecules, which will target them, bring them to the tumor. And once they reach tumor, there will be a drug also, or we work mRNA also, or peptides also, which will be act as a therapeutic way. So this is multimodality comes under good investigation, and that will be replacing our normal chemotherapy into targeted chemotherapy. In nanomedicine, it's huge actually the demand for such kind of therapies. Some nanomedicines are already in market. Some patients get it, but their effectiveness is still limited because it's not targeted yet. Many industries or clinicians are selling this under brand like Nanodoxil or others brand for chemotherapy or oncology, but still they are not effective. We need very targeted one into the tumor one. This is scientific part, our activation. I'll just stop this one and I will share the others. Just a minute, I'll share one also. Yeah. Let me see it. Oh, sorry, it's not here. I'll share this one. I hope it is not so much scientific. I'll be keeping
No, it's
more.
not. It's wonderful, actually. We get the
Now,
feel
I
very
was
nicely.
talking about the cargoes that what we are developing. So this is one example. This is an image, actually, it is very scientific image, but you might know about electron microscopy, which can give you the imaging up to nanoscale. Like what our eye has a limitation, we can see up to microscale, even millimeter scale. Then we go for optical microscope, which can, like our histopathology samples are optical microscopes. So they go into the some micrometer. But some samples are in nanoscale, like what we are developing, like lipid nanoformulations. So they are very nano and they are organic material. So when you use some high electric beam on them, they denature, they change. So we use the cryo electron technique in our lab to see them, because seeing is believing. So this is what we got, like around 50 nanometer to 100 nanometer drug. This is without drug and this is with drug. This is a liposome TMG, like this is a brain tumor drug with carrier. And we can see them like a layer by layer. Drug is somewhere else, carrier is there. And now we are going into the next level, like optimizing them. So we can target them. Also, we are using AI also. Two of my students, they are working on AI modeling. So what they do, they predict the disease behavior, more molecular features, also our cargo behavior, like where they will go, what kind of properties we need them, their stability into the blood, their effectiveness into the organs. With the database, right now we have, but we are generating our own database also. And validating model and predicting, develop our carrier with drug, how effective it is for any kind of uh, drug discovery. So now the third section is like how we are developing the 3D models. So as I said, like we are more on the in between to preclinical to clinical stage, are developing 3D models. So we are combining different cells together. And like in industry, what or in the earlier biological research, what they do, they always treat any into the petri dish. Okay, so the cells are there. You add the drug, every cell will get the uniform drug, and that will be killed or whatever. And then you comes, oh, this is 100% killing because cells are in 2D layers. You know? But in human, it's 3D multiple dimensions. So the human tumor is like this way. So they have layer by layer also. So the outer layer has enough oxygen in tumor, but when you go into the deep, no oxygen. At a certain stage, there is zero oxygen, but still that cancer cell survive. That is called the hypoxic condition. And in that condition, cells surviving, if you treat them and don't kill them, if they survive in that situation, they are very aggressive at a certain stage. And that's why when cancer relapse, return back, it's aggressive. There is no treatment for that because the harsh condition, the cells they get without oxygen, they survive. And once they come back, they are very, very aggressive. So we do not have model with a 2D layers. So we are developing this model or the 3D way where we can get these conditions, the less oxygen, other stuffs, and come to that. So this is what our models I can show you. It looks like different brain tumor cells, we combine. Like for example, breast to brain, there are two different cells involved. In brain also, we have neuronal cell, glioma cells. They are combining together. They are making collaboration and growing together for cancer, but not for other purposes. So why this is happening? We investigated how they cooperating each other. It takes time also, but we formulated industrial level way. We tested our formulations, drug, their efficacy. We still not have 100% killing in 3D way. 2D, we can kill 100% with our formulation, but 3D, no. And this is what we presented or investigated that why these drugs. Like for example, this temozolomide, we use almost 1000 micromolar. Okay? And even they are not killing 50% of the cells in a 3D way, compact nature. But even only 10 micromolar can kill the 2D cells easily. So almost 100 times higher, 100 folds higher, the drug concentration cannot kill the cells in a 3D atmosphere. That is why, again, our tumor is resistance because they don't get the enough drug. And even they get it, they're very resistant to the drug. We do actually, this is very simple doing the cell models. Actually, what complex is making the actual tumor conditions in a lab. For that, you need the either the patient samples, grow from patient samples, biobanks, or the tissues, and they will have the different breast cancer. They have 40 heterogeneity. So 40 type of different breast cancer cells survive together. So if we have the proper breast cancer sample, we can have this molecular heterogeneity there. Now we are growing them in a lab. We are making such kind of a model. We have collaborators even from USA, Oxford, and in-house collaborator. Also, we are developing with targeting agents also. So like peptide, the part of the protein chain, they can target our formulation to the specific tumor cells, not to the normal cells. So this is what our phase now. We are working on it. I'll skip this one. Yeah, this is very interesting. What we are now going into the next. So how fundamentally we are developing even combining biology and physics together and getting the new. Now, why this is interesting? Because in cancer, people don't know why they are aggressive. One theory is that these hypoxic cells are there, but they collaborate each other. Now, cell and two cells collaborate. For example, a tumor cell who got the drug, okay, and starting dying because of drug. Now, not all cells get the same drug concentration, localization. There will be some cells who are strong. They are the cancer cells, but they are survive without drug. They are strong. And one is dying. So there are two cells. One is a cell who doesn't have any kind of drug. And that cell will have all nutritions, all energies, DNA, everything is same. The other cell who got the drug, maybe their DNA damage, maybe their energy metabolism is not good, shape, everything, and they start to die. What happens? These two cells, if they come together or they are in close together in compact tumor, they are close actually. Now what they makes, they start signaling to each other. Okay, so the dying cell signal to the normal cell, normal cancer cell, that I'm dying. The normal cells and they make the tunnel between them. So they make the collaboration. Why? What they transfer? They transfer the nutritions. So like who is the main energy powerhouse in our cell is the mitochondria. So normal cell transfer their mitochondria to the dying cell. Now, when the mitochondria comes to the dying cells, they provide the energy. And then what happens? These dying cells may survive for somehow. And if they survive for long, that is what the tumor comes in aggressive nature. Now, this is what called the tunneling nanotube theory. And this is well proven in the brain. We actually identified them in a 2D nature, like this is 2D cells. and they are brain cells together. And they are actually making the tunnels, okay, between two cells. They are actually extending each other, communicating with. This is called the extracellular communication. They have intracellular, so the extracellular, and this is what not discovered, or the people were not focused more on that. The next is what happens in 3D nature. So one of my students, he comes from the MD Anderson and joined with me. Actually, he thought like in 3D, let's see, because we have 3D models, what happens? They make the tunneling nanotubes or not. And then he did the experiments and he found that, yes, in 3D nature also, they are making the very close tunneling nanotubes and they are actually transferring the mitochondria. Actually, we have results and unfortunately, I didn't include them, but we found even in the microscope that mitochondria is going from healthy cell to the weaker cells. Also, we use the Raman here again. Now, what Raman can give us, for example, this is an image. From image, though it is an image, there is no data. It's just image. Who will understand this image? Only the very expert guys. Until and unless there is no data, the common people, even the clinicians or the scientists, they don't understand. So the Raman is the only feature, the technique which can give you the information between the two cells or the cells who has this tunnel. So we did the Raman here, okay, Raman microscopy. We got some features, different nature. We did the Raman here also. One weak cell, one strong cells. We treated some cells with drugs, and we included the healthy cells there. So now they are making combine. And once they made this tube, we did the Raman also, profiling of Raman here also. And we got the different results. Even this is a single peak right now, but it has around, I would say, like 4 days we are completely running the machine to get the single spectra. This has the points of million points we scan on a 3D. And now we have 2 students who are working with AI/ML model, what exactly information is. Though it looks the same with tunnels and the normal cells, but actually the information is different on the molecular features. When we compare their lipids, proteins, nature, actually it is different. And this is what our breakthrough. We are writing now the multi-million project on that. We submitted the article also. I'm supposed to be published by the next month on this. We also did very good molecular antibody-based profiling, how these tumor cells commuting and making the transferring the nutrients. Now, why we are doing? Because if we know how they are commuting here, now break the relationship. Now, who will break the relationship? That is our cargo that we are developing. So we are developing the cargos which will target these tunneling nanotubes, not the cells. They will only be specific to the nanotube. Now, one of my another postdoc who came from the US also, he are developing these lipid cargos of very targeting agents, including that they will target this tunneling nanotube. So if we, this is the theory of divide and rule. Okay, divide their connection first, and then once you divide them by breaking them, again target the both cells. Okay, so until and unless we don't follow this divide and break rule, we'll not have the better cure for very late stage tumor, because where they have already tunneling nanotubes and all this. So this is very appreciated, and we received almost $500,000 funding last year, and we are submitting around 3 to 4 million funding for this year also on this theory, and with the proof of concept. And fortunately, we got very good collaboration from Tata Institute, Institute, Actrek Institute in the Kharghar, where we are developing the patient-derived models and identifying these kind of tunneling nanotubes. Also, we are developing the microfluidic chips, also screening the disease, especially in the Raman side, where we can have the pathological sample and we can get the more information. I will also come to the last of that this is what I'm showing. With Raman, actually, we can see some molecular level without any tag. So Raman is the only technique where you cannot use any dye or other stuff to see. Like for histopathology, you do the HE staining. So these are the dyes actually. When you add the dyes, they change the all nature of the cells, and you get the information, but this is not all correct. we use the Raman, we see cells actually and their molecular level without any dye, just laser. And laser is very weak intensive. So that cannot change the molecular nature of cells. So without any changing the behavior of the cells in real time. So even in real growth of the cells, we can do it. So this is another lab. We have actually very sophisticated lab funded by the European Commission. And fortunately, I'm in physics department. It is developed by the physicists for material purpose. But when I introduce my biological or clinical settings theory in physics department, they were interested. And we set up this almost 2 years. We got working with this. We got first image actually, which has a very high. Now we are going for the patenting the all setup and all. Again, I will come to the last. This is my group actually, which has it's old side, but I would say I have around 4 PhDs fully funded, 4 postdocs. They are also fully funded. Master students. I have bachelor students also. Also, I have MD students and MBBS students also in my lab. So I have physicists, I have biochemical engineers, molecular biologists, pharmacologists, AI/ML statistician we have, biomedical engineers I have, and then clinician like EMD people. They comes for research purpose. And MBBS students, we call here BMS degree in Ireland. And the 4th year student, they come for projects with me also. A very truly interdisciplinary group I have, research group. A couple of fundings I have right now, I would say more than 1 million. I am currently portfolio with my funding. Earlier, I managed 2 million also with different funding sources. And I hope it is more scientific way. But during the brainstorming, we can go for how I shifted this to this and how I trained to be as a learner, as a physicist, and trained to be a biologist. Yeah. Thank you.
Thank you. Thank you very much. That was wonderful, Nanasaheb. Well, the first question I have, Dr. Thorat, is when you make these experiments, you actually are looking at a live person, or you do it on cadaver, or how does that work?
So, for example, for cells, these are the cell
Yeah,
lines. So they already established.
I see.
So these are the cells like in the lab. So there is no patient involved. Usually,
Oh, there is a.
we grow them and they
Uh-huh.
fast grow. Like within 2 nights, you can have the millions of cells from
Oh
1,000
my God.
cells. Yeah,
Oh, I
yeah,
see.
they grow fast.
I
And
see.
then we test on them. So these are the cell line experiment. They're easy. The live to biobanks also. These are different nature. So like they from tumor samples from the patient, and they
Oh,
take time
tumor
to
samples
grow.
from the patient. Got it.
Yes, they take time to grow because the same condition. To grow the cell, you need to provide some media. We call it nutrients, other things also. The same nutrients you cannot provide them tissue samples. Tissue samples need different media, different reagents, different nutrients. From the live
I see.
patients or patient samples, you need different setting. And for cell lines or cells, you need a different setting. So we are working
So,
on both settings.
in general, the cancer cells can grow by themselves without staying in a human body.
Yeah,
They can grow
cells,
in the laboratory.
no, all cells, like even normal cells. If you take the liver cells and make
Oh,
the cell line means like the patient cells or the normal
uh-huh.
cells, they are growing again and again and again. So they change
Without
their
any help
phenotype.
from the human body, or without
Yeah.
any
They grown in
from
just
the.
lab. And so at a
Okay.
certain stage, they settle with that. And you just add some nutritions, they grow.
Oh, I see.
It's
So
like just,
that answers my next question, which was, do the cells die when the patient dies? Obviously, the answer is no.
yeah,
The cells can
even
grow even if the
and they
patient
die.
is dead.
Like even in the
Okay.
lab also, if you grow cells for cancer cells, like 2 nights is enough to get the double, triple population or million cells. But if you are keeping the media or the nutritions, you are not changing the media or nutritions for let's say
Correct.
5 days. The cells
Correct.
start to die also there. They
Uh-huh.
die. Even they
So
have nutritions,
human
but they
beings
die.
die when they die, when they have cancer. and they change the eating habits and all, that doesn't make whole lot of difference to the cancer
Yes,
cell.
yeah.
Got
Cancer
it.
cells behave differently.
Okay.
When you
Amitabh,
say that,
go.
yeah,
No,
when
go
you
ahead.
say that
Go ahead, Rajat.
the nutrition,
Let
oh, I'm sorry, yeah.
go
Oh,
ahead, Dr. Kotari.
this is a connected question, so I'll just jump in a
Yes,
little
yes,
bit,
absolutely. Go ahead.
So
Go
you
ahead, please.
mentioned nutrition, and I've heard that sugar is a nutrition that the cells
Yeah,
live on. So the nutrition that you would feed them to grow them, is that more sugar related?
glucose
Sucrose,
molecules. We sucrose and somehow glucose molecules we use them there.
glucose molecules.
And
Right.
yeah, because sugar actually get into the glucose at the end. So we
Right.
use the glucose, we use the FBS, portal serum also. And there are different parameters we use, like blood-like conditions for cells.
Mhm.
And why you might know why cancer cells love the sugar is that they need the more energy. Always they rely on the glycolysis pathway where glucose is converted into the ATP. And because they grow fast, so they need more nutrition. It means more energy. Only the sugar molecules, they can provide you the very high extent of energy within short time. And that's why sugar is one reason
Mhm.
for cancer actually, but
Mhm.
not always. But if you feed with the glucose molecules, definitely
Mhm.
they grow very fast.
What about fat molecules and protein molecules?
Yeah, the proteins are different. Like proteins are somehow nutritious also. They are the part of their cells, every cells. So we provide the proteins also to grow them,
Mhm.
to make different way. But proteins don't provide any energy to the cells. Only this
Hmm.
glucose molecule is the responsible which can provide the energy.
The
Proteins don't convert
caloric energy.
calories. Yeah, I would say like.
Yeah.
But for cells,
Mhm.
it is a molecules. They convert into ATP. For us, it is the calories.
Right. Okay. Right. Thank you. I'm sorry,
Okay.
Dr. Datta.
No, no,
I
no,
jumped in a
not
little
at all,
bit.
not at all. I'm learning from all everybody's questions as well. Dr. Thorat, firstly, thank you for your talk. I will confess that I have not much knowledge about cancer and cancer cells, so this was very interesting to me, and I'm still actually taking in something. I know I will go back and watch it again on YouTube to get a better understanding. But the last bit that you were talking about, the TNTs, the nanotubes. So
Yeah.
you said that your strategy is to try and break that up and then attack the individual cells, right?
Yeah,
So
exactly,
what
exactly.
is it that is actually breaking? What is the chemical or what is the thing
Can
that is breaking the TNTs?
Yes, that is very interesting. Like nobody has tried to break them. The people
Mhm.
discovered that there is a communication. But sometime,
Right,
working with interdisciplinary team, we
right,
decided to break them first time. Why we want to
right,
think that? Because they are a breach, and they are
right.
going everywhere. So we thought for aggressive tumors, like we have to break them. And this is what the thought process comes. We made the proof of concept. We got the proof of concept funding also, and we are going on the next level to get the
Also,
big
this is what
funding.
you're trying to do. You haven't yet done
Yes,
it.
yeah, yeah. But we
Okay,
identified how to break them, like
okay.
some kind of drugs can do it. Not drugs always, but we need some kind of peptides or maybe
Some agents.
agents which will break them. Yeah. Maybe
That's
physical
very
disruption
interesting.
works, but sometimes physical disruption always not work for whole tumor. More the chemical or
Right.
biochemical disruption works well. So we are thinking on the
Okay.
biochemical way to disrupt them, their
So this is
communication.
really your cutting edge science, if you will. No
I
pun
would say
intended. That
yes.
you're
If
trying to break through this TNTs so as
Yeah,
to manage the cancer's cell defeat. So you
yeah,
can
that's why
defeat
we
the
are going for
individual cells.
multi-million project to the European Commission. I'm
Well,
writing
all
actually
the
on it.
best to you.
Thank
I'm
you.
so happy that you talked about this because this is
And
absolutely
what we
new for me.
discovered actually, the earlier people just they know that brain cells only brain tumor they have the good TNTs. But my group has did the experiment on breast cancer cells, and we found in breast
Okay.
cancer also they are making the TNTs, and that's
Mm,
why
Okay.
nice.
yeah. The third we are going on to pancreatic cells, like what happening in pancreatic tumor also. And if we
Right.
get in pancreatic also, we are summing that all that. Okay, we'll
So
discover
you're
single
finding
medicine.
this is a link that
Yeah,
in all cancers,
maybe,
especially as you
yes, yeah,
say, the
yeah,
last stage cancers, they are
yeah,
having the same propagation method. So to attack those TNTs would be a way to cure or at least
yeah. And
retard the growth of the cancer,
what the
to
theory
slow
or
down the
the
growth. Right.
solution we are bringing, like we have, for example, painkillers. We have pain in the head,
Right.
we have pain in the knee, or other pains. What happens actually? We take the painkiller, everything for a short while, pain goes. Yeah, you take the
Right.
simple painkiller to the very high end. I think I don't forget the name, but
Prescription painkillers like
yes,
codeines.
yes, yes,
Yeah.
yes, 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 more things like that. But what they actually stop the signals actually. They don't stop the
Mm.
pain. They stop the signal to the brain.
So
This
you
is
don't
means
feel the pain.
yeah.
Right.
So that's what the universal tablet is. Yeah, that is called the universal
Right.
way. Now we are
Right.
thinking the universal our formulation as. So we will design a one formulation which will attack the multiple TNTs, which will attack the brain
Right.
TNTs also, breast cancer TNTs also, and
And the
the other.
pancreatic.
Yeah. So
Right.
for breast cancer, you don't need the different formulation. For pancreatic, don't need. So our formulation, somebody has a brain cancer, give them. Somebody has a breast cancer, give them. Somebody has a pancreatic, give them. So till now we are
Right.
succeed that breast cancer, brain cancer, making it. Hopefully we'll find this in the pancreatic. Or if we don't find, what will? Still we are writing the project that
Right.
even in the pancreatic we will investigate it. That we investigated in
Right.
these two.
Right.
Oh, they are there.
Right. Not finding
Hopefully,
it will be just as exciting as finding it, because then
yes,
that tells you
yeah,
that the different kinds of cancer cells. Right.
yeah. And then
It's
other
it's
people will
really
jump on that.
interesting. Yeah. Thank you so much. I learned a lot from your talk today. So
Very
Thank
good.
you.
thank
Yeah,
you.
good job. Good job, Dr. Thorat. Rohit, do you have a question or a comment?
No, no. Actually, since you're from Limerick, I sent a limerick about the Bhagavad Gita, but
I didn't
I
think
did
of
find
that.
I
Yeah, I saw
actually
that.
I do have two people who have cancer, and I don't know whether it's terminal or not, and I do feel sorry that I didn't include them to attend this talk. But there's going to be the video, right? So
Yeah.
I can send them the
Yeah.
It's going to
link,
be on our YouTube channel. Yes.
and then they can attend your talk, right? And I think it was really very interesting about the different kinds of cells.
Well, actually, we still work in the lab, very fundamental and somehow applied. We approach some industries, one of the top industry from Netherlands who designed the patient-based samples
Yeah.
formulation, the mini tumors. They came forward to collaborate with us. One formulation industry from Ireland, they came forward with us to go for joint venture. But it takes time because I'm trained to be a fundamental scientist. I'm physicist, so physicists are not really good money making or businessers. So they always have, even Elon Musk. Elon Musk has a physics degree, but physicists always love the fundamentals way of discovering something. Yeah, so I'm trained to be like
Right.
physicist, not a clinician. So I would be a clinician. Might be I will have my own venture. But as an
So
academician, we have limitations also. We have many theories, but it's very difficult for an academician to translate something, to get the industrial exposure. And somehow we think that making money is one way, or translating to people is another way. But teaching, where you train the next generation caliber,
Of
you design
researchers.
like,
Yeah.
yeah,
That is
next
its own
generation research.
reward.
Yeah, that is what the reward is. Sometimes your all theories will not work for patient. Okay, you cannot cure patient, but you are actually making the next level scientist, or the encouraging the young minds to come
Yes.
forward. So like in
Right. To
physics
explore
lab,
other
we got the medical
possibilities.
students to come and do the research. I don't think this because in US or in European setting we can do it, but in India it's very difficult. In physics, you will get the medical student will come, or physicist will go in the medicine. I'm physicist and I know like treating cells, and the physicists don't like to go in the biology. They will
Right.
never go there, and biologists will say,
they don't like biology, that's why they learn physics too.
Yeah.
I'm just kidding. I'm just kidding.
No, that's
But,
true actually. That's why
Very
they
yeah.
true.
love.
Yeah.
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 But
Well,
That is true. I remember now my Elphinstone days, I was terrible
Wait,
at
I
the
wasn't
fog
finished. I
dissection
wasn't
and
finished.
stuff like that. I would wait for the physics experiments, which I was good at,
hmm,
with the light and sound and
yeah.
well, yeah,
it's
yes,
good.
Rohit, go ahead.
Thank you.
Rohit
Yeah,
bhai,
no,
you were not
I had a
finished, you said?
question. Since
Okay.
you have been to Poland, I
Yeah.
thought I've been in correspondence with a Polish computer scientist, and he was complaining that Poland is losing a lot of its talent to the West, right? I mean, of course, Poland, you could say it's a European country, but not quite as right. And
Yeah.
so I wrote to him that India has the same problem, and actually, you see that there are 5 or 6 of us, all of us with PhDs, all of Indian origin, and all of us are in the West, right? And so I suggested to him that there could be an Indo-Polish institute where Indians and Poles could collaborate together. But maybe there could also be a kind of a collaboration with Ireland, because Ireland has a
We are
historical
lobbying for that.
similarity to us.
Yeah.
That because they were also oppressed by the
British
British,
colonial.
same that we were, and
Yeah.
so they must have some
You,
common.
even our flag is same actually. We just have to revert, and then it's a
Hmm.
Irish flag.
I see.
So when somebody asks me this question about brain drain and all this, my
Yes.
straightforward answer always is that because I do science, and
Yeah.
you know what is the difference between science and technology?
Yeah.
Like technology, someone owns it. Yeah, we call
Yeah.
Japanese technology, we call German technology, we call US technology, Indian technology, Chinese technology, yeah, Israeli
Right.
technology.
Yeah.
We never say like it is Japanese science, German science, US science, British science,
Yeah.
or Indian science. Never, because nobody owns the science. We never have the Newtonian science, Einstein science, nothing. You know, it's science. And that's why
Yeah.
I'm more love with science, because science doesn't have border. Wherever you do the experiment, discover something, it is for whole world. So though I left the India almost 14 years ago, but I still
Yeah.
love science and I do the science. I know if I do the good science, maybe Indian will benefit in the future, not this generation, maybe next generation. Yeah, because it is science. Nobody can claim that this is my science and I like Newton's laws. But
Yes.
before Newton, there was laws actually. Earth is moving around the sun, everything was there. He just discovered the mathematical relation. And that is
Right.
what people thought Newton's laws. Then Einstein theory of relativity. There was a universe actually, and they all following the relativity and all this, even our molecules. Einstein discovered it, but nobody thinks that this is just Einstein's science, or because Einstein was in Germany and then went to the US because he discovered all theory of relativity. That's why this science is only owns to the Germans or the Americans. Never. That's the beauty of science. Once you discover and keep it open to everyone can
Yeah.
jump and do the research and criticize you, going to the next level. That's what we are doing. So that's what the best theory. If you do science anywhere in the world, it is beneficial to everyone. It takes time to translate them as a technology. Once somebody has to come and owns it, yeah, from mobiles to the even the medicines. If you have the highest dominance by the US pharma industry, from Pfizer to Merck to the other industries, Regeneron, all this is right now in the gene therapies also. But what science they are using? They are using the science by the worldwide people. That's not
Yeah.
what their science. They just making the proper branding or bureaucratic science. Actually, technology is what it is. Like when we write the manuscript and publish it, it's open one. But when in the same time when we write the patent, it is very bureaucratic. Even we don't like that language as a scientist. So
Yeah.
I hope like in future, like when we talk about our countries, I do much of talks, I go anywhere. What difference we have actually? The
Yeah.
main is our freedom actually. We are unfortunately very bureaucratic in science. If you think about politicians are doing politics, I would say openly, go into the research labs and see the politics there. You will say like politicians are
Has
far
its
better
own
than the
politics.
scientists.
Yes.
Yeah,
Yeah,
politicians are
that is
far
true.
better than scientists. that what nasty politics they are doing in the
There is a
science.
lot of
Yeah.
politics in labs.
Lobbying,
That is
they
true.
do the lobbying,
Uh-huh.
favorism, the pseudoscience they are doing, no proper experiments, funding fraud, the everything they do. Actually, what
Yeah.
politicians are doing it, they do that. So this is one problem. It's not the India's problem. It's the universal. In every country there are these problems. Even in the
Yeah.
South Korea, you might know, like the story that professors, they what they're writing when they're submitting their papers, publishing their papers, they were including their child's names there.
Oh my God.
Why? As a
Child's
co-author.
name.
Yeah, their kids who was in university education in their papers. So once, because they will say that, oh, my son has the already some 2, 3 publications, then they will get the some maybe uh, more money for that, or maybe a good admission in the good or the good industry jobs. But this is pseudoscience actually they are doing. So even South Korean people are doing, and they get caught, they fired.
Mm-hmm.
Many of them punished it. So even we believe that science, the Korean technology is best, but people is everywhere. They are doing the same business. It's not a country's problem;
Right.
it's the universal problem.
Very
It's
Agreed.
good.
very
Simple
interesting
problem.
that you said, it's very interesting you said that scientists are worse than politicians in this regard. So
Yeah,
that's really
I,
quite a statement.
because
Because I
uh,
know a lot of politicians here and they are pretty bad, but I've also seen and come up, been involved with a lot of
With pretty bad
scientists.
scientists.
And I see,
Right.
yeah, I see the same. Yeah, I see that there too. I have a
It's a good
question about,
analogy.
yeah, it's a good analogy. I have a
because if
question
they make
about,
the lobbying actually, they start with lobbying
yeah,
first, and what
yeah,
politicians doing, the politicians actually openly doing it. Everyone know
yeah,
that they are
that's
doing it
right.
to
Yeah,
their favor. But
yeah,
scientists usually they do to keep their people on chair, or maybe suppressing someone is very superior than
yeah,
me in security
right.
fields. Like I'm 40 years old, for example, and I went to one of the private university in India for a talk, and the vice
Mm-hmm.
chancellor didn't attend it. What he said, like, I'm 65 years old, I'm vice chancellor, why I will attend this guy? But he's a what his ego superiority feels that I know you are a vice chancellor, but you are in the same institute for 30 years. Okay. I am in 7 different institutes within 14 years. I sit on different chairs. I know the different cultures. I know the different institution policies also. I work in Oxford. I know the Oxford policies. I'm working in
Mm-hmm.
Ireland. I know their policies also. I work in Korea also. I work in India. So better how I know the what Oxford policies are there for HR to the science. I know the Korean policies for science to the research, or I'm in Ireland or in Germany where academicians and the science policies I work. So if you work in the same institute, sitting on the same chair for 30 years, you design or you develop policies, but sitting in the same institute, you do not have the exposure for multiple institutions, multiple countries, multiple culture, multiple bureaucratics also actually. That I have. So then the people has the ego problems. I from whom I most learn is I from my students actually. I sit with my students instead of my seniors or all this, because they will not talk science. They will talk about politics, department, and all this. But students don't know about this. They always talk about science. So I learn more from them actually. Whatever I learn as a physicist, or more biology from my students actually and my colleagues. They teach me actually, oh, this is don't work. You think in this way, but no. Actually, here is the problem. The clinicians, I have clinicians on board also, with whom they work with the patient for 10 years. So they always think, so no, inpatient, this is not a way. Patient has the different scenario. But I have core fundamental scientists also. They think, oh, patient has that, but in lab we cannot replicate it. We cannot make it. Lab has this problem. So, and I learned that, oh, patient has this issue, but lab has this issue also. So actually, we have the people in science, they don't like to learn
Yeah.
from our juniors.
You feel that this morality problem or honesty problem was not so bad, say 100 years ago in Europe or in other places compared to what it is now. And I mean, I see here, and forgive me for some people who may not agree with me, but in climate science,
Yeah.
I have seen a lot of people who are trying to do it for fame,
Yeah.
for funding, for that kind of things also at the same time, and going through pseudoscience, as you mentioned.
That happens in
So
clinics also. Like people manage the clinical trials also. Their results also in favor of the
right,
pharmaceutical industry.
Yeah,
yeah,
I think
right,
the
yeah,
pharmaceutical drug industries sponsor them, so they give
Yes,
them
yeah.
money
yeah,
to have the
Right.
favorable
That
results.
is sad but true. Yeah.
yeah, yeah. One question I had was, I've been hearing about all these things, radiation treatment that we have now, and this is not exactly in what you are talking about, but it might be related, and you may know the answer to this. Um, for radiation treatment, they use gamma rays mostly,
Yeah.
and like that, right? But now they're talking about using alpha particles
Yes.
for radiation treatment, which can be more specifically. Now, what I've heard is that alpha particles can not go through even the skin or a paper or something like that. So, how is it that alpha particles can be used for this, and does that also help in your research in some way or the other to do this using alpha particles?
Well, in a radiation therapy, when we talk about radiation, that is high energetic rays. They start from
Right.
X-rays and then alpha, beta,
Mhm.
gamma rays. Gamma is the high energetic, but they have more penetration power. Then
Yeah.
beta rays. Particles actually, the rays and particles.
Mhm.
Now, particles
Right.
always beneficial because they can burst something, you know. But the problem is that penetration, as of course. When we can
Yeah.
solve it, if we have a probe that will guide this particle to the tumor inside, and then
Oh.
excite with the radiate with the particles. While in gamma rays, you don't need that probes. You have the machine,
Yeah.
and they can be
Senior.
very localized on the tumor and they are high
Hmm.
energetic. So if it is localized, they can kill somehow. Or they don't actually kill 100% tumor. They shrink the tumor. So sometimes
Yeah.
clinicians, what they do, depend on the tumor size, they decide should we go for chemotherapy first or radiotherapy first. So sometimes they go for radiotherapy cycle first to shrink tumor initially,
Hmm.
and then use the chemotherapy because
To
then you can
to
use
destroy it.
a lower
That's
dose
right.
of the chemotherapy,
Hmm.
and then they go for surgery most of the time. Or they
Mm.
can do the reverse also. For breast cancer, usually they go for surgery, and for remaining
Right.
tumor, they go for the radiation therapy. For brain
Right.
also,
Okay.
they do the same uh, surgery and radiotherapy protocol use. In some
Hmm.
cancers, they do the colon or others where they first go for radiation, then chemo, and then surgery. So this alpha beta will not be working. Alpha is working. Yeah, people working on that. But until and
Hmm.
unless there is no probe which will guide them to the tumor,
Yeah.
there is
Hmm.
interesting also, like I was talking about light also. So light can destroy the tumor also, but from not
Mm.
outside. You need some specific probe, like laser, like we have the what we use that for screening of the heart blockage.
Endoscopy.
Endoscopy, yeah.
Right.
Similar
Endoscopy.
type of
Yeah.
the laser
You
probes.
need to
Now,
put in the wire with the probe at the
yes,
end.
yeah. Now,
Hmm.
somehow I know US military has such kind of probe that can go into your liver also. Yeah.
Mm.
So they can, with the laser, you have camera also, and a high energetic laser. If you guide them into the liver, tumor especially, you can kill them. Yeah, or the
Let
easy
them
accessible
targeted.
tumors. Yeah.
Right.
Okay. Yeah. And the
Interesting.
last
Yeah.
question is, yeah, the last question is, you had mentioned that this talk is about multidisciplinary approaches and stuff like that. When you say multidisciplinary in this case, you are talking about biology and physics, basically, medicine and physics.
Actually, see, like I do biology, I'm physicist, but there is a connecting bridge between physics and
Yeah.
biology is chemistry. And
Oh.
you have to translate something, then it comes to the engineering. So like what medical device industry is actually physics based
Oh.
industry. Any medical device, stethoscope, I teach that subject, medical devices. So from physics to the stethoscope to the MRI machine, the most complicated medical device right now. They all rely on physical principles. Stethoscope, sound waves converted into, or mechanical waves and all these converted. In MRI,
Right.
actually magnetic field make echoes by your hydrogen molecules in a brain or in the anywhere in the body. And these hydrogen molecules with the high energetic field, they flip. They make the transition from paramagnetic to the ferromagnetic side. And when they make the transition, that is what they industry. Yeah. So they have stethoscope to the MRI, they physics principles. Now, who took the benefit? Engineers, actually. Physicists know that with the magnetic field, hydrogen in the water, hydrogen in the brain or the body is flipping. But engineers made the things happen.
Device.
Device. And who opposed it? Clinicians. MRI was not in clinical terms. Was clinician thinks that this is high magnetic field and we are not going to use it. Same with the X-rays. X-ray wait for 30 years. Ultrasound has the same story. But now without ultrasound or X-rays or MRI, there is no diagnosis, for everything, not in the US or Europe, but in India, whatever happens, go for MRI. I have knee pain, I have even the pain in the ears, let's say, they will say, oh, go for the MRI. So everything their business is.
Yeah, it's become common, like
and people don't need like clinical settings in radiation field, because I teach medical physics also. We know like a single patient is not allowed 2 cities per year. At max 5 cities per year. Max 5 cities, because they have X-ray radiations. But in our side, like one hospital, you do the city, go into the other places. Oh no, in our hospital, you have to do again the city. They don't know the regulation. Like you are treating that, though you want to diagnose it, but you are for 2 minutes you are giving the X-rays. You don't know the high energy. They can damage the DNAs, and that might be a triggering for any kind of cancer.
For other disease, right?
Yeah.
Other cancers.
So this is what actually the clinicians do. They make the business, but actually the fundamental scientists, they don't care about it. They discover something, the advantages to others. Like for physics, from semiconductor to solar cells, is physics discoveries. Engineers get benefit. In clinics also, like stethoscope to the MRI, clinicians gets the more benefits. But in multidisciplinary, nobody cares about now. Though whatever your field is, it's coming together. Even we use the psychology also. You need the economics also. There is a health economics concept now coming. China is starting health economics. That is very different.
Not just China, US has been doing it for a long time.
Yes. So this is what, like, when you go into the patient level, maybe their economical condition, how they affect on their treatment also. For example, I have theory about it, how economics play a role in the clinics. So, for example, 2 people who is one of the more rich and one of the poor, who every day has to go for the work, 500 rupees a daily, and the rich guy who maybe $1 million business every day, and they both have the same, like suppose have the body pain, okay, and they want to stay in the home for a day. That one guy will lose 500 rupees, or other will lose the 10 lakh rupees, for example, because he's rich. Will go with the same doctor. They will have the same problem, but different economic conditions. They will ask, okay, doctors, I can be stay in the only 1 day in a home. I cannot next day, because it's our brain and water problem. So you have to give the best medicine for us to treat this all, whatever disease or pain or something within a day. Now, if you compare this on a placebo base, they will be get cured in the 1 day also with the same medicine. They different have genetic makeup, but they have the same economical mindset, because I cannot lose something, though as coming from poor background or rich background. So this is what economical theory is playing major role. Even I consulted with many doctors and they said it's true. Like when people comes with us and they says, oh, we cannot stay more than 1 or 2 days in the home, give the best medicine. And when we give them, they don't come back. Either rich people and poor people also. So actually, this is what the economics playing major role. We don't know, we don't discover, or we need more research also on the social science base or economical base. Probably we will have better medication prescription for the patient.
Very
Yeah.
good.
So I'm
Okay.
more actually so much. I think brainstorming is there. Yeah.
Thank you so much,
No
Dr.
problem.
Thorat. I have to go
No
to
problem.
another
Thank you
meeting.
very much. Very good.
That the
Well,
world is
thank
very
you very
small.
much for
Like,
doing this.
yeah.
This was wonderful.
Thank you. Wonderful. Very, very illuminating
Very, very,
and
very
very interesting.
educational.
Yeah.
And thank
Okay.
you.
Bye.
Okay. Bye bye. We'll see you.